Denis Firsov, and in this presentation I'm going to tell you about probabilistic reflection, rewinding of adversaries, and coin toss protocol in EasyCrypt theorem prover. This is a joint work with Dominique Unruh. Let me start by giving you some background on EasyCrypt. EasyCrypt is a theorem prover for verifying cryptographic constructions where protocols are specified as imperative programs and adversaries are modeled by abstract program modules. EasyCrypt has four logics: a probabilistic relational Hoare logic, which is able to relate pairs of procedures; a probabilistic Hoare logic, which allows one to carry out proofs about the probability of execution resulting in some post-condition holding; an ordinary Hoare logic, and also an ambient higher order logic for proving general mathematical facts and connecting judgments in the other logics. Most of the time, these program logics are sufficiently expressive to carry out the usual cryptographic proofs based on game rewriting. However, sometimes we find ourselves in situations where the security proofs of very simple protocols become challenging. Before showing an example of a challenging proof, let us review notation. We write probability expressions which consist of a program, initial memory, and a predicate. Here, the program is a procedure P of a module X. The module X might be stateful. Here, the initial state is represented by a memory configuration denoted by little m, and the results of the computations are tested against a predicate m. The security of a coin toss protocol, which will be discussed later, at some moment requires us to prove the following theorem. Let A be a probabilistic rewindable program. Here, rewindable means that module A has procedures getState and setState. The getState procedure must return some value S, which must be an encoding of a state of the module A. And setState S should restore the initial state of a module A. Let us review the inequality. The program of the probability expression on the left starts with the state initialization by A. Then the state of module A is stored in the variable S. The procedure A main is run once and result stored in the boolean R1. Then the module A is rewinded by resetting its state to S, and the procedure main is run second time and the result is stored in boolean R2. We are interested in the probability of an event when both computed booleans R1 and R2 are true. The claim is that the described probability is lower bounded by a square of probability where the state of module A is initialized and then the main procedure is executed only once and it returns a boolean true. The proof consists of only 4 steps. Step 1 applies the averaging technique by representing a procedure A init as a distribution of final memories, given that its execution starts in memory M. More specifically, the mu1 expression under the sum is the probability that procedure A init terminates in the memory state N, given that it starts in the initial state M. Notice that the rest of the computations under the sigma are run starting from memory N. Step 2 makes use of the fact that the probability of a success, in other words that procedure A main returns true, in 2 independent runs equals to the square of a probability of a success in a single run. Step 3 is an application of Jensen's inequality. The final step undoes the averaging. There are a number of challenges in formalizing this proof in the EasyCrypt. For example, the proof turns the program A init into a parameterized distribution of final memories. In other words, memories after A init procedure terminates. Also, EasyCrypt doesn't have a type memory, so we cannot define a distribution over memories. Moreover, the proof makes use of results about probability distributions, for example, Jensen's inequality, which we believe is hard or even impossible to prove directly using program logics. Finally, it is not immediately clear how one can generically specify the interface of rewindable programs, which can return their own state. In our work, we resolve these issues by making the following contributions. We develop a method for reasoning about probabilistic semantics of programs inside EasyCrypt. We call this technique a probabilistic reflection. Also, we design a set of tools to address rewindability in the EasyCrypt framework. Finally, we validate our results by developing a formal proof of a coin toss protocol based on rewinding. Recall that in EasyCrypt there are no valid types which refer to distribution of final memories after we execute a procedure on some initial memory. However, in EasyCrypt, each program has an associated variable glob_am, which we denote by writing capital G indexed by module A and memory M. This variable represents the part of the memory M which is accessible by module A. So, effectively, the semantics of a program can be described by looking only at the part of a memory accessible by that program. We define a family of distributions which, given an initial memory configuration, assigns a probability to every possible final memory reachable by that module. The main result of probabilistic reflection can be summarized by the following theorem, where A is a module, main is a procedure of A, M and fin are initial and final memory configurations respectively. glob_am and glob_a_fin are values corresponding to initial and final states of module A respectively. D is a family of distributions describing probabilistic semantics of procedure A main. In the presented equality, the mu expression describes the total probability of final states reachable from initial state M which satisfy predicate M. In other words, for any program there exists a distribution which precisely captures its probabilistic semantics. The main importance of that theorem is that it allows us to access the distribution which corresponds to a program to derive probabilistic results which would be hard or impossible to prove by using only program logics. However, being able to reflect the distribution corresponding to a given program is not enough. Given a composite program A:(B, reflection gives us distributions DAB, DA, and DB, relating to the semantics of A:(B, A and B respectively. However, we do not a priori know how DAB is related to DA and DB. In our formalization, DAB is shown to be the monadic bind of DA and DB. This result allows us to precisely reflect the semantics of composite programs based on the semantics of its parts. In our derivation of a security of a coin toss protocol, we used probabilistic reflection to derive some well-known results from probability theory. For example, we proved finite probabilistic approximation, which intuitively shows that for any procedure A run, there exists a finite list which contains the result of computation with overwhelming probability. Also, we proved the averaging technique, which is widely used in cryptography. The idea is that if the program starts by sampling an element x from a distribution D and then passes x to the rest of the computation, then the probability expression which corresponds to this program can be expressed in terms of the probabilities which correspond to individual elements from distribution D. It is important to note that here the support of D might be infinite. Finally, among others, we proved the famous Jensen's inequality, which also can be frequently encountered in cryptographic proofs. Now we move to rewindability of program modules. Formally, we say that a module A is rewindable if three conditions are satisfied. First, there exists an injective mapping F from the type of state of module A to some parameter type S bits. Second, the module A must have a terminating procedure getState so that the execution of getState in state M must return its embedding without changing the state. And finally, the module A must have a terminating procedure setState so that whenever it gets an argument X of type S bits and the preimage of X corresponds to a valid state of module A, then it sets the module into that state. In our work, we showed that the assumption of rewindability is not a restriction on the set of possible adversaries. If the rewindability is defined correctly, then there are a number of intuitive properties which must be provable for rewindable modules. For example, commutativity shows that we can execute procedure run 1, then rewind, and then execute procedure run 2, and this is the same as executing procedure run 2 first, rewinding, and then executing procedure run 1. Multiplication property shows the independence of runs after the rewinding, namely executing procedure run 1, rewinding, and then executing procedure run 2 is same as independent executions of these procedures. Now we move to the coin toss protocol. Manuel Bloom described the idea by following example. Alice and Bob are recently divorced, living in two separate cities, and want to decide who gets to keep the car. To decide, Alice wants to flip a coin over the telephone. However, Bob is concerned that if he were to tell Alice the result of his coin toss, she would adjust hers and automatically tell him that she wins. So the problem with Alice and Bob is that they do not trust each other, and the only resource they have is the phone communication channel, and there is not a third party available to read the coin. Let us describe one possible implementation of protocol which achieves fair coin toss suitable for the described scenario. The protocol starts by Alice sampling a bit B1 uniformly at random. Then Alice must generate a commitment on bit B1 and send it to Bob. We can think of commitment as a strong box which contains the bit B1, and Bob cannot open or see the contents of it without the opening key. After receiving the commitment, the Bob samples a uniform bit B2 and sends it to Alice. Finally, Alice sends an opening key to Bob which reveals the bit B1 to Bob. The result of a protocol is a bit obtained by XORing the bits B1 and B2. It must be clear that if both parties are honest, then the protocol works out perfectly. Also, if we assume that commitments are perfectly hiding, then Bob has no way of cheating against the honest Alice. However, the situation with the cheating Alice is more interesting. We want to show that if Bob is honestly following the protocol, then for any cheating Alice, the protocol generates almost random bit. We start by pointing out that if Alice is potentially cheating, then we don't know if the strong box contains a truly random bit or something maliciously constructed. Let us assume that Alice wins the game when the result of the XORing the bits equals to 1. To prove the security of the protocol, we go through the following mental experiment. We start by running the protocol once and getting a yellow opening key which opens the strong box so that it contains a bit B, and by our assumption B XORed with B2 gives us bit 1. Now we can rewind Alice and run the protocol second time, but now we send negation of B2 to Alice. To win, she must produce the key which opens the same strong box to a value B prime, so that B prime XORed with negation of B2 equals to 1. Clearly, this happens only if B prime is a negation of B. Hence, if Alice succeeds in both runs, then we have a situation when she opened the same strong box to contain bits B and the negation of B. In cryptography, this is known as an attack against the binding of a commitment scheme, and these types of attacks can only happen with negligible probability for any reasonable commitment scheme. In our development, we formalize this proof and show that if the commitment scheme is binding and if Bob is honest, then for any cheating Alice, the protocol produces a random bit modulo negligible error. Thank you for your attention.